I had this question, and it's why are there two tides per day? So I did a little AI search, and a BBC, like a Google BBC, gave me some bad explanations. I did not like it.
Okay.
You want to see why?
Let's see why. I'm curious.
Here we go. Here's the AI overview. So first we see this picture. Here's the Earth. There's a bulge on this side. This is like the moon side, and this is the other side. And the explanation was that there are two high tides per day because of the interplay between the moon's gravity and the Earth's rotation.
Okay.
Okay.
Because at first glance, what you'd think there's one bulge on the Earth,
Yep.
the one facing the moon, but there's like a
Exactly.
second bulge on the opposite side, and you're like, what?
Exactly. I mean, it seems right. Like this side is easy to explain. The moon pulls the Earth and also the water, and so it pulls the water towards the moon. You get a little high tide there.
Yep.
The other side is the one
sense.
that's not so easy to understand.
Yeah.
Okay, so let's push on with the explanation. The moon's gravity pulls on the Earth, creating a bulge of water on the side of the Earth facing the moon. Seems right.
Okay.
A similar bulge occurs on the other side of the Earth due to the centrifugal force caused by the Earth-Moon system's orbit around a common center of mass. As the Earth rotates, any given coastal location will pass through both bulges, resulting in two high tides per day.
Okay.
So I can understand the second sentence, and actually, this for me, first time I learned this, I was like, "Oh my gosh, brain explode!" It's not so much that the tides are running around the Earth; it's more that the moon pulls on the high tide, and the Earth rotates underneath the ocean, or I guess like the swells.
Right, because the water stays with the Earth's surface as the Earth rotates. It's the bulge itself that moves along the Earth's surface as it rotates.
Right. And so it's not like the water molecules are ripping around the Earth, or even that the Earth is ripping around underneath the water, but it's like the accumulation of water that creates a bulge.
Yeah.
Okay. So for the near side of the Earth, that makes a lot of sense. Seems right. Gravity pulls the high tide. You get a high tide here, and then wherever you are at the time, if you're there, you got a high tide. The far side is a confusing one. So the description, it is bulge occurs on the opposite side of the Earth due to the centrifugal force caused by the Earth-Moon system. So I guess what is first the centrifugal force?
Well, my understanding of the centrifugal force is if you go into a non-inertial reference frame,
Yeah.
then
Hate it.
you feel a fake force called the centrifugal force.
Yeah.
And I think the best example is if you're rounding a corner in a car,
Yeah.
you feel like you're flung to the outside of the vehicle.
Perfect.
But actually, if you go in, that's in a non-inertial frame because the car is accelerating.
Right.
But if you go into the inertial frame where you're looking out like a bird's eye view from the Earth, then there is no centrifugal force. Your body wants to go straight, but the car gets in the way and pulls you around the corner.
Right. So if I can understand that, if I can reiterate that to you, it's you're going straight, but whoever the driver is, they're turning. And so but I mean, you're going straight, but it feels like you're getting, say you're turning to the left, it feels like you're getting pushed to the right, but it's actually because the car is pushing into you to the left. Like the car is making its left turn, but you going straight compared to that from your perspective feels like you're getting pushed outward. But that cool, I understand you. But that can't be a real force. That can't be something that's actually happening. Because one of our rules from Newton's, I guess, third law is that you have a force of A on B and B on A. They have to have the equal magnitude in opposite directions. In this case, if you were to be in that bird's eye view, like what threw you to the outside? There's nothing threw you out there. So it's not a real force that actually did that. It's like your perception from the fact that you're the car that you're in, you're like the frame that you're referencing is accelerating. It's non-inertial.
Right. So I think when AI here is saying centrifugal force, it's implying we're doing this analysis from a non-inertial reference frame, which is super weird.
I hate it. Like one of the rules we have in physics is like go to an inertial reference frame. Like that's the first thing you do. Otherwise, all the force is going to be weird because it's not actual forces that you're dealing with. You're dealing with the whole frame, like your whole reference frame, your whole perspective is sliding around. Don't do that. Don't do that.
Well, okay, but I will say sometimes, maybe, in some scenarios, going into the non-inertial reference frame may be simpler.
That's a good point. That's a good point.
Like if it's easier to solve the problem in the non-inertial reference frame, switch to the non-inertial reference frame, do your stuff, and then if you want to, bring it back.
Like the math is easier to do in the non-inertial reference frame, and as long as you transform back correctly, okay.
I think so.
I hate it. But you're right. Like as long as you do it correctly, okay.
Right.
Okay. So what I don't like about this is that we have to invoke a fictitious force, like I want the real, like object A acting on object B and object B and acting on object A. Like I want the real, what is actually happening between molecules, between atoms, or gravitational scale is fine, but I want the actual objects identified. Which centrifugal force, it can't do that.
So what does this paragraph here say?
The Earth and the Moon are gravitationally bound, and orbit a common center of mass. I'm cool with that. So it's if in the limit of like the Earth and a human out here, then the center of mass is pretty much in the Earth. But in the limit where the Moon becomes pretty big, which the Moon for planet systems, our moon is very large compared to our planet. Then the average location of the mass, the center of mass, is not in the middle of the Earth. It's somewhere a bit off center.
Yeah.
I don't know if this is true. If it's, I know for the Pluto and I guess Ceres.
No, it's Pluto Charon. I don't know how to pronounce it.
Oh,
Charon.
Sharon. One of those.
Charon.
Where Pluto and its moon are really similar in size, then the center of mass is in the middle. So instead of being like center object and then another object going around, it's really like they both go around a center point right in the middle. Okay, so I think that's that sentence says. It's, they are gravitationally bound, they're stuck together, and they orbit a common center of mass.
Yeah.
Inside the Earth, but not in the center. This creates a centrifugal force on the Earth, which pushes outward on the side of the Earth opposite of the Moon, which also results in a bulge of water.
So, gosh, I don't like that at all, because, okay, we could go to a non-inertial reference frame, which, where are we right now? Because we're in a non-inertial reference frame.
You're saying because Earth is traveling in space and going around the sun, so it's actually also not an inertial reference frame?
No, I'm saying that this analysis for sentence 2 here must have been done in a non-inertial reference frame. But instead of this explanation saying that we're going to be in a co-rotating frame or something, it's just stated, centrifugal force causes the bulge. Like, what? Where did this come from? Because it's not actually there.
Yeah.
So what?
It's not an actual force, and so you can't actually identify the objects, which means you're just asserting it. Like centrifugal force, that's what it does. But prove it to me. Show it to me. Like, walk me through it.
Yeah, I mean, because... because now I'm lost, because I don't know what frame we're in. I don't know... This is a non-explanation for me. Right.
And so there's also the centrifugal force of the Earth rotating. And there's going to be some drag in the ocean from the ocean floor and all the coastal lines. But that should sling out water in every direction.
That's right. I mean, okay, it should sling water out every direction in a cylindrically symmetric manner.
Yeah.
Right. At the equator, it's going to be the most slinging outward.
Yep.
And at the poles, it'll be the least.
Agreed.
Okay.
So this was an unsatisfying explanation to me. I mean, it feels okay, but it relies on this fictitious force, which I cannot put my finger on for like what is actually causing the atoms to move the way they do.
Right, because what I would like to see is start with the inertial reference frame, transform to a non-inertial reference frame, and you pick up a centrifugal force along the way, and then that centrifugal force is causing the bulge. But
then you got to be able to bring it back.
Then you got to be able to bring it back
and identify the actual forces that are causing it.
Exactly.
Doesn't happen. They jump to a frame, we're like, yeah, it makes sense, but you can't jump back.
Okay, but to be fair, this is like an AI overview,
Right.
so it's not going to get into that.
So that's why I was like, let's get another source. So this was Sky and Night magazine, space science, two times a day. I didn't clip it, but it said BBC up on the top of the page. So, and so here's this picture. So here's the Earth with the moon, and here's the gravitational force at every location. And
Looks
so, and here, right dead on center and close, you get a big long arrow, strong gravitational force. The gravitational force behaves like 1 over r squared. The closer you are, the stronger. Further away you are, the weaker. Seems good.
Okay.
And then out here, the same idea. You get a stronger force when you're close, weaker force when you're farther away, and they're angled in towards the moon, always radially towards the object. Cool. So, and here's the explanation. The moon's gravitational pull on the oceans is stronger on the side of the Earth closer to the moon than it is on the opposite side. Gravity is 1 over r squared, so closer, stronger. But there's another force, which is the same everywhere on the Earth's surface, that opposes the moon's gravitational pull, called the centripetal force. We've now introduced a third force. Let's get to that. We say the moon orbits the Earth, but actually they both orbit a point that lies within the Earth. I think it's the barycenter. I'm not sure if it's barycenter, if it's still inside the object, but barycenter, it's the center mass point. The centripetal force is the force that keeps the Earth moving in a small circular orbit around this point.
Okay. Cool with that, I think.
Okay. So first, what is the centripetal force? The centripetal force is also it's also not a real force. Like you cannot give it this name of like object A pulls on object B, and then therefore object B pulls on object A. There's only a singular centripetal force. There's no like opposite of it.